Assalamualaikum and a very good day. My name is Muhammad FARIS bin Morris, and today our group would like to present about the tomato leaf disease classification using convolutional neural network. So next, here are my group members. Now I would like to give a brief introduction about our system. Tomatoes, one of the most widely cultivated plants, are a nutrient-dense fruit that provides farmers with a significant source of income. However, various leaf diseases can harm tomato plants, reducing yield and quality. Early detection and natural treatment of this disease are critical for effective disease management. So, this project aims to develop a practical and scalable solution for agricultural disease management. This project also focuses on the categorization of tomato leaf disease using deep learning, a type of machine learning that excels at picture identification. As a result, understanding the causes and effect of this disease is critical for maintaining crop health and productivity. Thereby, using CNN, we can create robust systems that are capable of classifying various tomato leaf disease with high accuracy, assisting farmers and agronomists in timely intervention and disease management. So next are the objectives. The first objective is data collection and pre-processing. We aim to gather a diverse dataset of tomato leaf images, including healthy leaf and those affected by various diseases. The next objective is model development. We aim to design and implement a CNN architecture tailored for image classification tasks with a focus on distinguishing between healthy and diseased tomato leaf. The third objective is training and evaluation. We aim to train the CNN model using the pre-processed dataset, employing techniques such as data augmentation to improve generalization. The last objective is deployment and application. We aim to develop a user-friendly interface or web-based system to deploy the trained model, enabling farmers and agriculture professionals to easily diagnose tomato leaf disease.
Okay, now we will discuss about data collection methods for our system. For this project, the data collection method for the tomato leaf disease, we are gathered from the one main source, which is from the Kaggle website. The dataset we found contain of 11 tomato leaf disease, and the total numbers of images is 25,848 images. Out of the all 11 tomato leaf disease, we pick only 5 type of disease that we think are suitable. For example, we pick the early blight, healthy leaf mold, powdery mildew, and septoria yeast spot. Okay, as you can see, the first one is the healthy leaf of dataset. The second one is dataset for the early blight. The third one is dataset for the leaf mold. And the fourth one is dataset for powdery mildew. And the last one is dataset for septoria leaf spot. Okay, for the informations, we have made an extractions to filter the corrupted files that are contained in the dataset, because the image that we get from the Kaggles contain a few or some corrupted file. So the models cannot train it properly. So in order to remove it, we have made the filtering and delete it from the dataset. After that, the process of training will begin smoothly. Okay, for the whole dataset, we have divided into 3 files. The first one is for training file, second one is testing file, and the third one is validation file. Okay, for the whole image of dataset, we divide into 3 percentage, which is we take the 80% of the dataset used for the training, and we take the 20% for the testing, and also again we divide 20% of the testing, we divide it into a 10% used for the validation. Okay, for the trainings of the dataset, we use the convolutional neural networks, which is the CNN method, and the number of epoch used in the system is 60 epoch, and the best size we use is 32. Okay, now we move to the system flowcharts of our system. In order for users to use the system, they need to start the system, and then the initialization of the flow applications will begin. It will integrate with the front ends application, which is for our system we use the index.html, and that is will display the interface. User needs to upload an image to begin the predictions. After the user upload an image of the 5 classified image that we mentioned earlier, the image will be processed by the CNN models to predict which classes those images begin. It will predict the 5 type of image that we have trained, which is the healthy, early blight, leaf mold, powdery mildew, and the last one is septoria leaf mold. And if the system or the AI found the image, it will display the predictions of the results and the accuracy of the result. If user inserts the image other than 5 types of images that mentioned earlier, and the system will display image not found, and it will ask the users to upload the image or re-upload the image again, and the process of the CNN model to predict the class will begin again.
So next we will be moving on to the model architecture. So convolutional neural network CNNs are deep learning models that extract features from the images using convolutional layers, followed by pooling and fully connected layers for tasks such as image classification. So there are 2 main parts to a CNN architecture, which is feature extraction and classification. A convolutional tool that separates and identifies the various features of image for analysis in the process called as features extraction. So as you can see for the diagram, convolution was the first part. So this layer is the first layer that I used to extract the various features from the input image. In this layer, the mathematical operation of convolution is performed between the input image and the filter of particular size. So next, the network of feature extraction consists of many pairs of convolutional or pooling layers. So the aim of pooling layers is to decrease the size of convolved features map to reduce the computational cost. This is performed by decreasing a connection between layers. So for the last part is fully connected layers. A fully connected layers that utilize the output from the convolution process and predict the class of the image based on the features extraction in the previous stages. Next, we will be moving on to the sample input. So figures on the left shows a sample input interface of the system. To initiate the process, the user must click on choose file button. Upon the clicking, the system will open a file dialog window, allowing the user to navigate the folder containing the image that they want to predict. The user can then select the specific image file that they want the system to predict. So this step is crucial as it enables the system to access the image data necessary for making a disease prediction on the tomato leaf. Next is the sample output. So figure on the left illustrate the sample output interface of the system. So after the user upload an image and click on the predict button, the system process the image and display the results. This output includes the prediction disease affecting the tomato leaf and the confidence level of its prediction, expressed as a percentage. The confidence level indicate how certain the system is about the accuracy of its prediction, providing the user with a clear understanding of the reliability of the results.
So for the test and evaluation, the accuracy rate and also the learning rate will be defined to show how well the CNN model was developed, as well as the error rate, recall, and precision to see how much the model's performance increases over the training period. So for the accuracy rate, we have the training and validation accuracy as well as the training and validation loss. So if you can see here, the training accuracy starts to increase below the 0.3 mark, and validation accuracy actually starts to decrease almost near the 0.3. So it keeps on increasing over each epoch up until the 60 epoch, which has 0.95 at least for both training and validation. And if you look here, we have the training and validation loss. So the training and validation loss starts to decrease near 1.6, and it just starts to decrease over the 60 epoch, and it ends at around at least 0.2. So why is the training and validation accuracy increasing? So the reason why it increased is because our model keeps on learning, and as it learns and improving on its accuracy, it makes the classification for our tomato leaf disease more accurate. So this is also why our loss is decreasing, because as it becomes more accurate, the time for the model to run to predict the data set decreases. So for our learning rate, the epoch that we use to test this 15 epochs, and throughout the 15 epochs we receive the learning rate at 0.0010, and it's consistently that value from epoch 1 to epoch 15. So why is the epoch have consistent 0.0010? This is because having a fixed learning rate helps to maintain a steady and controlled weight updates in the model, and it can avoid potential issues that may occur during the training process. For the error rate, over the 15 epoch, it starts to decrease over time. So if you see at epoch 1, it starts with 1.5657, and over time it just decreases. Here you can see in epoch 2 it has 1.4589, and it decreases up until the 15 epoch, which is 0.5388. So overall, the data shows that it has a steady improvement in the model performance, as evidenced through the progressively lower error rate over the epochs. So the recall is actually used to evaluate the effectiveness of the model, and it used to measure the model's ability to identify all the relevant instances within the dataset. And hence, overall, it shows the data to steadily improve in the model's performance, as evidenced by the lower error rate over the epochs. And lastly, for the precision. So if you can see here, our precision starts at 0.8027 at epoch 1, and it goes to 0.8135 at epoch 2. And if you see up until epoch 8, it stays just at 0.8, which reflects a high accuracy rate in the model's predictions. This variability indicates that different factors during training affect the model's precision, suggesting potential areas for optimization to further enhance the model accuracy. So here is the demonstration, but before I do the demonstration of our tomato leaf classification, let me show you a bit of the coding. So here I use JupyterLab. So here I use TensorFlow and also Keras. So I define the image size as 256 and the batch size as 32. And for the channel, this channel is 3 because we are doing a colored image. So, and then the epoch used for this project is 60. So here we define the dataset, and this part is just to display the images inside our dataset. And here we define the train size for us to train the data. So here we split 80%, and then we take 20% as the testing. So here the data will be split. So here we have the train split as 0.8, which indicates 80%, and the validation split to be 0.1 for 10% validation for the training, and the test split to be 10% also, This is the reason why the test split is 0.1 is because we split the validation and also the testing, which has initially the testing have 20%. And then we try to resize and scale the image, and we do some data augmentation where we rotate the images to ensure that we can have a very accurate definition, a very accurate classification. And then here we define the model. So the total layers that I use are 1, 2, 3, 4, 5, 6. So the total layers that I use for the model are 6 layers, and after we define the layers, we flatten it out to make sure that the classification is accurate. And then here we compile the model, and this part is just to check if there are any invalid images that we do not need. So here is the model fit, which is the training part of our machine learning. So for the epoch, we set it as 60 previously, and the batch size as 32, and this validation data. So after that, we can get the accuracy over here, and then to check the training, validation accuracy, and also the validation and training loss, we use this. So, and then this one to test if our model can predict the images. So here we have one image. So this picture is supposed to be healthy, and the predicted label is healthy. So meaning our model is quite accurate. And this part is to showcase the accuracy for multiple images. So here we set as 9 images. So if you can see in the first image, it predicted as healthy, and the actual image is healthy, but the second image is a bit wrong. It's actually early blight, but it predicted as Victoria. So the model is quite inaccurate, but it's still usable. Now on to our web application. So here is the coding for it. So we use Flask, and we extract the model. We load the model that we saved previously. And here, if we use this, it should open this. If we run this, it will open the HTML file where we can use it to classify the tomato leaves. So if we choose, for example, if we choose this image and we click the upload and predict button, it will show us the prediction as healthy and the confidence level as well, which is 51.61%. So if we try another image, for example, let's say this one, it will predict it as healthy. And if we try another one, let's try this one, it will predict it as powdering mildew, which is correct. Even the previous one is correct. So that is all for the demonstration. Thank you.
So in conclusion, this project demonstrates the effective use of a convolutional neural network to accurately identify tomato leaf disease. By employing advanced pre-processing and augmentation techniques, the model achieved 100% accuracy in classifying healthy and septorial leaf spots leaf with an overall accuracy of 90% for other diseases. Integrating this model into a user-friendly web application enables real-time disease diagnosis, benefiting farmers and agriculture professionals. Furthermore, improvement will aim to enhance the model generalization and reduce misclassification, especially for the powdery mildew class, showcasing deep learning potential in agricultural disease management.